here. So Fabrizio received his PhD from Roma 3, I believe.
No, Roma 1.
Roma 1, sorry, Roma 1. Okay, from Roma 1, some time ago. And then after that, he moved to CFA. He was working at that time on AGM. But after he discovered the first tree in the forest of the intergalactic medium, he was pursuing two areas of science in parallel. After CFA, he got a permanent position at Montepulciano. And in the meantime, he had a stint here for 3 years, I think 2010.
8 to 11.
Okay, 8 to 11, okay. And after that, he's visiting more or less every year or every few years, minus the pandemic.
Minus the pandemic, right.
So today he's going to tell us the latest about trying to discover the missing baryons and trying to find more trees in the intergalactic forest. Okay, how is it?
Thank you very much, Andreas. Got it. Thank you, and it's a pleasure to be here again after 4 years, actually this time. If you wonder what the logo in, and if you don't wonder, I don't care, I will tell you anyway. On the top right is nothing to the affiliation. That's the logo of AS Roma, my football team. Actually, it is an old logo of the 80s. So, okay, what I will tell you is not exactly about the missing baryons in general, it's the missing baryon or the universal missing baryons in the universe. It's about missing baryons in galaxies. And the problem of the missing baryons in galaxies is actually very much related with the problem of how feedback in galaxies manage and if it manages to quench star formation. They seem to unrelated problems, but actually they're very much related. So let me start with the I think I should click, no? Here, perhaps. It doesn't move. Yes, okay. I will start with this slide of Roberto Maiolino that is working on this problem of feedback and quenching of star formation in galaxies. And it's a diagram that essentially shows the cause of the possible causes of quenching of star formation versus the mechanism that do it. And the one which I think is the, but there is now a certain consensus about this. The mechanism that I think is more efficient in doing this is actually starvation or strangulation, as they call it. So essentially, you don't get gas into the disk as much as you want. The problem is, does this gas actually enter the galaxy at all? And if it enters the galaxies, where is it? Because, and this is the problem of the missing baryon, because it's certainly not in the disk and not in stars. The problem itself of missing baryons, the fact that there are no baryons in galaxies, not as many as there should be, this doesn't move. Okay. It actually can be seen in these. Now, if I show the, yeah, they will see. In this plot, this shows essentially the baryon mass in galaxies versus the stellar mass, which is here at the top, or actually that is halo mass. It's not the stellar mass. It's the virial mass of the virialized object that can be anything from a dwarf galaxies to a cluster of galaxies. And this plot shows that actually when you count baryons in these objects, actually you have for the most massive ones, you are okay. In clusters of galaxies, we know that the baryons that should be there and the baryons that should be there are essentially the universal fraction of baryons in the universe. This is a cosmological parameter which is quite accurately measured actually in many different ways. And we know that it should be about 17% of the total matter in the universe. Now, in clusters of galaxies, we actually count most of these variants, which are in a hot infracluster milieu, mostly, and partly, but a minority in galaxies, in clusters of galaxies. But then when we go down in halo mass, actually the deficit of variance become more and more evident. So the question is, where are, and already, I mean, if we take a galaxies like ours, so a typical is called L-star galaxies with an L-star luminosity, which is where the log s actually bend the log s of galaxies. These luminosity typically corresponds to halo masses of about 10 to the 12 solar masses. Our Milky Way is 2 times 10 to the 12. They should have this mass of variance 1.6 times 10 to the 11, and instead what we see in stars is only a very small fraction, 3 times 10 to the 10. So there is about 4 times, 5 times the mass in stars, which is missing. So the problem is, where are these variants? This is also from a paper from Maiorino. This other plot that shows only why somehow the two problems are related, because not only we don't see variance in galaxies, but also in the disk of galaxies, it seems like there is a shortage of gas. So there is no gas to actually form star. In this case, for massive, this is stellar mass now. For massive galaxies, there is a shortage of this color-coded fraction of variance in gas, and there is very few gas in these galaxies. So, all in all, the problem is that there are no variants in the disk. They are not in stars. They are not in gas. So the question is, where are these variants? What hydrodynamic simulation predict, and it's actually a very easy prediction, because if you got a halo mass of 10 to the 12, you expect baryons in this potential well to virialize at some point, and the virial temperature of a 10 to the 12 solar mass halo is 10 to the 6 Kelvin. So it's a very high temperature, a million Kelvin degree, and baryons in this at this temperature, of course, are heterogeneous, practically fully ionized. You expect some residual opacity from light metals, but the question is, are there any metals in this gas? If there is any gas in the halo of the galaxy, which there should be, it should be hot. The problem is if there are metals or not, and there may be metals. If you imagine this gas is accreting from the IGM, so it's a relatively primordial gas, especially high redshift. But then, most likely, since if it is in the halo, it's bound gravitationally to the galaxy, so it gets enriched probably by the galaxy itself through stellar winds, AGN winds, and so forth. And this is what we call feedback. So studying, actually, first of all, finding baryons in these halos, see whether they actually account for all the baryons, and what is the metallicity, and whether they can explain any of the feedback, and so the problem of quenching of star formation. It's all open. It's one of the most open problems in astrophysics nowadays. So this is to justify the study. The other thing I want to show you here is that we know nothing about this hot gas. We don't even know if it exists. But we know for sure, there have been many studies in the last 10 years, that there is cold or mildly ionized gas in clouds in the halo of galaxies, up to the virial radius, or perhaps even beyond the virial radius. The virial radius of a galaxy of 10 to the 12 solar masses is about 250 kiloparsec. So it's a very standard halo. Compared to the disk, is at least 10 times the size of the disk. These cold clouds have been studied a lot with the technique is these essentially. You take, so there should be you take a quasar in the background. This is your satellite that observes. Whatever is in between imprints absorption lines in the spectrum. And if you catch one of these halo near the galaxy, you would see absorption lines in your spectrum. So now this is the one of these cases. This is the quasar in the background. This is the galaxy. And at the distance, which is your impact parameter, in this case, 130 kiloparsec, you see these absorption lines. These are H1 and mildly ionized silicon in this particular case. This is a magnesium 2 line. Actually, this probably is the galaxy. I don't know, I'm not sure. No, this is a spectrum of the galaxy. So, of course, at the same redshift of the galaxy and at this impact parameter, the galaxy is associated normally to the absorber because the same redshift, they choose typically a delta V of 50 kilometers per second or so. So it's at the same redshift of the galaxy, and it is normally the closest one. The galaxy that is associated to the absorber. Whether this is correct or not, but it's the easiest assumption and hypothesis that one can make. And in most cases, it's probably the correct one also. So this is how they detect these cold clouds, photoionized clouds, mildly photoionized clouds of gas, photoionized by the external radiation field. And this is also something we are not completely sure about. But anyway, there have been many surveys which have studied these cold components of the galaxy halos. And here you see one of these studies. These are all the absorbers, these are Riemann limit systems. So they are systems which have column density in hydrogen between 10 to the 16, 10 to the 15, 10 to the 16, or even lower, 10 to the 12 to 10 to the 15, I think. Per centimeter square. So you can you have all these absorbers. You can try to do some physics out of them. For example, you can plot the column density of the H1 absorber versus the distance in units of virial radii from the galaxy, which is associated to the absorber. And you see that there is a smooth decrease of column density with distances. But still, column densities are pretty high. Actually, this is the equivalent hydrogen column density of the order of 10 to the 19, 10 to the 20, even at one gravitation, one virial radius. The other thing that you can do, you factor the coloring factor depending on how many of these objects you find per lines of sight and so on and so forth. And in the end, you can try to estimate a fraction of baryons in this Hot-CGM. And the fraction of baryons that is estimated is about 50% of the missing baryon, on the previous missing baryon. So the bottom line is that even if this calculation is properly done, I would say even less than, no, it's 30%, I'm sorry. It's properly done. There is still a lot of mass which is missing. So the responsible probably is this Hot-CGM, which I showed you in this sketch before, this brownish part of the halo, in which this cloud should be embedded and perhaps in pressure equilibrium with the hot gas. Now, the hot gas, if it is realized, is probably in I can find the word, I'm sorry. In equilibrium, hydrostatic equilibrium, and at the virial temperature, as I say. So the relevant questions, I think I already listed them. What we want to know, first of all, we want to find this gas, this hot gas, if it is there. And then, of course, we want to try to study all the physical state, the dynamics, and so on and so forth. Why is so difficult to find this gas? Because as I said, it's very hot. So it doesn't, you cannot see it in hydrogen absorption because the hydrogen fraction is 10 to the -7 of this temperature of the neutral hydrogen. So you cannot see like an alpha or any other transition from hydrogen. You could start to see metals. In particular, oxygen is the most abundant metal in the universe after hydrogen and helium. So it's the most promising. And oxygen at this temperature should be in the oxygen 7 hydrogen helium-like ionization state. Mostly in the helium-like ionization state, also because helium-like ions are very stable because they're helium-like. So do we see, or have we ever seen these oxygen 7 transitions? Well, in our galaxy, yes, since now at least 2002, as Andrea was saying, we published the first evidence of oxygen 7. This is by far the best X-ray oxygen 7 we detect, but it's a very strong line. Now the thing is that in our galaxy, not only is easy because we sit in the galaxy, so any line of sight we observe, us must show this oxygen 7 line if there is some hot gas in the galaxy that produces it. But we don't know, we cannot know where it is. It could be in the disk, it could be in the thick disk, in an extended halo. We always suppose that this must come from either an extended halo or corona, or even the circumgalactic medium, so the local group of galaxy. But these are still, I mean, cannot really be proven with the resolution of the X-ray instrumentation we have now. And the other difficulty, actually, this brings me to the other difficulty in searching these lines. The problem is that to search for this line, you need X-ray. This is an X-ray transition, 21.6 angstrom. You need X-ray spectrometers with high resolution and high collecting area, because these lines are very weak. The equivalent width is of around 10, 20 milliangstrom expected for these common densities. So it's very difficult to detect. And
Fabrizio,
yes,
this is also detected against
quasar. This Markarian 41 is a blazar very nearby. But it doesn't matter because.
So why do you say that you cannot pinpoint the location of the absorption? It has to be against the bubble.
You know, it's a redshift 0, but whether it is the local bubble, the disk of the galaxy, I mean, the line of sight crosses everything. So you know it's around the galaxy. Redshift 0 is around the galaxy. I mean, the resolution of this instrument is 500 kilometers per second. So the line is probably known 100 kilometers per second, but you cannot say more than that. A different thing is that if you observe an external galaxy, as I showed before, in these cases, you observe an external galaxy, your quasar, you know, it passes at some point at this redshift, of the galaxy redshift from here, you know the distance from the galaxy. So you know whether this is passing through a galaxy or at 130 kiloparsec from the galaxy. So you know for sure that is halo. So the next thing one can try to be sure that there is halo gas, hot halo gas in galaxies, is to do exactly what they've done with HST. But HST is a much more powerful spectrometer in the UV. We don't have so powerful spectrometers in the X-rays, probably, and hopefully they will be coming in the next 10 years or so. We hope a bit earlier, but so with what we have now, we can only try to exploit the archive and stack and proceed by stacking, which is what I'm going to show you now. What we did was to take one of these samples of Lyman limit systems that they detected in the UV. So we know for sure there is gas near to some galaxies at those redshifts because it has been seen. It's cold gas, it's not the hot gas we know we want, but we use this as a signpost because we know that around these clouds, there should be also hot gas. So if the line of sight goes through one of the cold clouds, he also has to go through the hot gas. We searched the archives. In the end, to make a very long story short, we were able to select only 3 sources actually associated to 3 galaxies. 3 of these had XMM RGS observation, gradient observation, and 2 of them also Chandra observation. This is the total amount of observing time for these objects, about 2 megaseconds. So, and these are bright sources. I mean, of course, this is what is left after you throw out all the sources with not enough signal to noise in the Chandra LTG or the XMM RGS. The galaxies associated to these Lyman limit systems actually are these 3. These are the property of the galaxy. These are the impact parameter of the Lyman limit system. We average these things by weighting them for the signal to noise in the X-ray spectra. And these are the average quantity we get for what we call the X-ray halo. So it's a 120 kiloparsec distance. The halo has a virial radius of 192 kiloparsec and a mass of about 10 to the 12 solar mass. This is the stellar mass, but it doesn't matter. With that mass of the halo, the virial temperature expected is exactly 10 to the 6 Kelvin. Now, the first thing we did was to see whether in the single source there was a hint of this oxygen 7 K alpha line in absorption. And there was a hint, but just a hint, in all the 3 of them, actually, at the redshift, of course, of the corresponding limit system. These are 1 sigma to 1.5 sigma detection of this line. So we proceeded to the stacking. First of all, you put the spectra onto a common grid, you direct shift them to the redshift of the Lyman limit system, and then you stack them. And by proceeding in this way, and you're stacking from the highest redshift to the lowest redshift Lyman limit system, you see that you get a signal increasing in exactly at 21.6 seconds. So when the oxygen 7 line is expected, this is the corresponding K beta transition of the same line. And also, I mean, the only 2 amplified signal by the stacking were these 2. This is again the same spectrum shown now in ratio to the continuum as showed in standard deviation. This is the oxygen 7 K alpha signal, oxygen 7 K beta, and maybe a much lower significance, something at the nitrogen 6 and K alpha and K beta. Nitrogen 6 is of course also expected in gas at 10 to the 6. This is again the spectrum, now in counts, not in standard deviation. What we did was to average, build a response matrix, line spread function for these RGS Chandra stacked spectra, and we fit the lines. This is the strongest by far line in the spectrum, oxygen 7 K alpha. These are the significance, the contours of the line in equivalent width versus wavelength. So there is the oxygen 7 is detected at 4.2 sigma, and the nitrogen 6. Here we say 1.7. This one 2.1 sigma. It's actually because these are for one interesting parameter. So it looks like 3 sigma, but it's actually 2.1 sigma. The total, if you go out in quadrature these 4 line signals, you get a significance of 5.3 sigma. So with these lines, with equivalent widths, what you can do is to derive ion column density. As I say, the resolution is quite poor for these X-ray spectrometers, so you don't really resolve the lines. So you cannot, you have the ambiguity, the degeneracy between the Doppler parameter and the column density. All you can do is run curve of growth and try to constrain the column density and the Doppler parameter of the lines. So in this plot, you see ion column density versus Doppler parameter, and these are the constraints we can get from K alpha and K beta transition of these two lines. Those are the numbers, but it doesn't really matter. What we assume here is again, it's pretty unconstrained, especially well, both column density and Doppler parameter. But for these objects, we use the Doppler parameter, the average Doppler parameter of the oxygen 6 transition that is seen also in the far ultraviolet for this Lyman system. Not compatible with the photoionized clouds because it's oxygen 6 is higher ionization, but it's seen in each of these three sources. So, and the average Doppler parameter is 80 kilometers per second, which is what we use. With this column density, you can now try to constrain the equivalent hydrogen column density. We assume the average metaviscity, which is observed for the Lyman system. Again, it doesn't have to be the same, but it's in the same environment at the same distance for the galaxy, and the average was 0.3 in metaviscity for these systems. We use only actually, this is the constraint we get from the UV oxygen 6, for which we use only as upper limit as the nitrogen 6. Because oxygen 6 may actually is probably not produced exactly by the same gas that produces oxygen 7, so we use it as oxygen as upper limit. The important thing is this blue line, which is what actually gives you a lower boundary to the hydrogen equivalent column density. And this is the set by the oxygen 7 detection that we have. So all in all, we get a temperature between 10 to the 5.8 to 10 to the 6.3, and this equivalent hydrogen column density 10 to the 20.15 to the 20.77. These are quite high column density, and it translates into well, this instead we consider also the nitrogen 6 associated to this, not as an upper limit, but associated to the same gas producing oxygen 7, you get this smaller region interval of parameter, which, by the way, whose average is exactly 10 to the 6 Kelvin. This is just some physics you can derive from here. You can derive the real temperature, of course, which is 10 to the 6, which, well, no, the real temperature of this halo is 10 to the 6, and the agrees it falls in the interval of temperature that we measured. The density of the clouds that you simply derive by, well, it's a bit more complicated because there is some assumption on this covering factor, which we take to be complementary to the covering factor estimated for the photoionized lines. You get a density between 2 and 8 times 10 to the -4. This implies, with this temperature, this kind of pressure. And if you compare it with the pressure estimated for the cool clouds, these photoionized clouds, is actually quite different, an order of magnitude different. Now, this means that either the clouds are not in pressure equilibrium with the hot medium, which is weird, or that actually photoionization is not the main mechanism of ionization of these lines, which is very much discussed, because these pressures, these densities are derived for the cool clouds under the photoionization assumption. Now, having said that, with the hydrogen column density, hydrogen equivalent column density, and the impact parameter that we know, we can run beta profile models for this halo for a number of values of the parameters of the beta profile, which is the central density, the core radius, and the beta parameter. And for, in particular, for an isothermal halo, which is this blue region in this plot, you get this mass of the halo. This is in unit of baryons which are still missing from these halos. And it's clearly 1. I mean, this is the value we can in this Steiner region. This is the average value we get, which implies that these are all the baryons that are expected to be within the gravitational potential of the galaxies are actually in, if these measurements are corrected, at least for galaxies with this is a bit slightly sub L star galaxy. Now this is quite important because not only because the baryon seems to be there, but also because there are reasons to believe that they shouldn't even be there. They should be probably farther from the galaxy, not bound to the galaxy, because if there is enough feedback to quench star formation, there should be also enough feedback to bring these baryons away, at least in the hypothesis in which AGN have a strong impact, which I think is not the case. This is the summary, but I want to go to this slide, because what I think is that baryons are actually all generally bound to the galaxy. They have accreted at the rate which they should have accreted according to the cosmological baryon fraction of baryons. And if that is the case, probably what quenches star formation is two things. The first thing is that actually you cannot accrete more because you have this halo of gas, which is called strangulation. And the second thing is that you don't expel gas from the galaxy because they are all bound into the halo. Now, so why doesn't this material keep falling down to the disk and form stars? Because in order to do that, it needs to cool. And cooling time at these densities are very low. And of course, they can be shortened if you metal enrich the gas, and the gas is quite metal enriched. I mean, this is the metallicity we find in the gas, but still the cooling times are very short, are quite long. So it takes time. So what we think is that simply what's going on is that the star formation is actually very much slowed down. And so in the end, probably quenched, because and the residual contribution from feedback could be on one side to increase the metallicity and to shorten the cooling time, but on the other side, you are injecting energy through these winds, and this actually heats up the gas. So it's a combination of these two mechanisms that probably halt and prevent star formation. These are hypotheses, of course, and with this I stop.
So, questions?
I have one question related to it seems that you found all the baryons in this hot component, but you said before that you have found 30% in the cold component.
No, including when you take those out. When you take those out.
So that one is the addition of the components.
This psi is defined as the mass we find in this hot component divided by the universal baryon fraction times the mass of the halo minus the star mass and the mass estimated for this cool CGM. So when you take everything out. Sure.
Okay, so we have another question.
At the beginning, you said that you said some archival data, and you used the available galaxies, you follow the stacking procedure, right? In the stacking, show that you can make science. I mean that you show the line.
Yes,
after the stacking.
yes.
So my question is, did you submit any proposal for larger samples in order to follow the same procedure? Because
I mean-
stacking.
I didn't, now, because I'm old, I'm against proposals. I'm against proposals because these are satellites which are flying since 99. So it's 23 years. HST also even longer, but it has been refurbished and they changed the instrumentation. So it made sense to keep doing science. To me, making proposals, so this stack spectrum is 2 megaseconds. So you either ask for 10 megaseconds, which honestly I would give it. If the science is interesting, I think after 23 years, I will use these satellites for 10, 30 megasecond observation, 1 year, who cares? But they don't do this because they have to serve the community to very, how it's called?
Democratic.
No democratic, yeah, but what can you do after, what can you do with a 50 kilosecond observation of the 100, 200 source after you observe 199 exactly for the same reason, exactly we will say 50 kilosecond, what can you do? So this is the reason I don't do proposal, but if you want to put proposals, you need enough time. So I actually honestly believe that the archives need to be exploited. I mean, these missions have flown for 23 years, and in general, not only X-ray missions, archives are full of things that needs to be exploited.
I missed a little bit the way that you made this selection. I mean,
Because I didn't say it. The selection is actually so there were in this particular, I took 2 samples of cool absorbers, 33 sources. Of these 33, 11 had Chandra and or XMM observations. Of these 11, I downloaded all the data. 7 of these were, can I say shit? Online. Yes. The remaining 4, actually, the remaining 4 sources, 3 of them are the ones you saw in the stacking. Another one, I used it in the beginning. It wasn't an extremely, it was a signal to noise of 4.5 compared to 25, 13, and 10, whatever. But he actually he made the signal worse. He didn't have any if you looked at the X-ray spectrum of that source, there was no hint for any line. And when you go up, when you start also the 4th source, he made the signal worse. I was of the opinion of leaving there also this source because it showed that stacking is dangerous, because if you stack things which all have a signal, the signal amplifies. But of course, if you stack things in which 80% of the source have no signal, the signal completely gets washed out, you don't see anything. But I think it was instructive. Then we submitted this thing to Nature. Nature sent it to the referees. One referee, so the paper is not now is in Nature Astronomy, but because one of the referee was very against the paper, and for personal reasons, we believe, no main science objection. But the other referee had actually quite good suggestion, and one of these was to take that source of the sample because he thought it was useless. So now we don't consider this 4th source anymore. But this was a selection.
and there is the possibility of stacking on sources that don't show good absorbers.
But then you don't know which redshift you should search for the line. I mean, when you stack, you have to redshift other. You need a signpost.
Yeah, you do it when any other line in the optical. I mean, you know the galaxy, you know that you should
But-
get so.
Yeah, but you know the galaxy. You don't know whether there is any gas within the virial radius of the galaxy.
It should be under.
No, okay, but you are right. In fact, actually, people before us have done this with galaxy only, by stacking galaxy, large concentration of galaxies at the redshift of the galaxies, and they couldn't find anything because actually I think it's not surprising because you really need to look for the. I mean, these are. We know there is gas at 150, 30, 100 kiloparsecs from the galaxy. We know it for sure. It's cool. It's not the same medium that we are looking for, but we know for sure that there is gas there. So we know we go and look directly there.
Okay, makes sense.
So if I may ask a question regarding the photonization. So you mentioned that there is a problem with the pressure equilibrium and possibly the optically identified clouds are not photoionized. So it's what is called linear ionization, such as reaction?
No, there are I think now the trendy thing is dynamical ionization by motion.
What does that mean?
I don't know. I don't understand. These clouds move into the medium,
Okay.
into the hot medium, and they get ionized at some level. I don't understand why they don't get either completely washed in the hot medium or, but apparently is. I don't know. I should study this thing more. I don't know. I don't know why they claim
The
this.
motion-based ionization, that's
Right. The other thing is that they use even if it is photoionized, they use cloudy model, equilibrium model for these clouds, and I'm not sure that would work. That necessarily is the case. So, and by the way, these densities have a spread of about at least one of their mind.
And then the other question is, if it's photoionized, what is the source of the UV photons?
External, metagalactic.
Ah, okay.
Metagalactic. Of course, you have because all these are galaxies, not active galaxies.
Yeah,
So
yeah,
there is no
yeah.
AGN around.
Yeah, that's what I was wondering.
What
Okay.
is it?
All galaxies. I mean, the UV background that you have in the universe is given by galaxies. But this is light, which if they meet a cloud with a very low density, they ionize.
So it's the average intergalactic UV radiation field. So, and another question, so you, in the end of your conclusions, you mentioned that most likely this gas is primordial gas that is involved in the cloud, within the galaxy, but the metallicity is quite high.
Yeah, in it
So
will
what
be,
is that?
well, we are a redshift 0.12. So we are in the local universe. I'm not
Okay.
saying that the IGM is 0.3. But you are around the gas.
Like
But you are around the gas. Well, the infracluster medium is 0.3. The actually you have a floor at 0.3. I
But
mean,
this
it's
has
very-
been erased by the galaxies themselves.
right, and well, but you are very close to a galaxy.
So,
there.
so it's like the chicken in the end. This was the end point of my question. How do you know that this gas is not coming from an outflow from the galaxy and is coming from primordial gas?
Well, it has to accrete from the gas has to accrete from in a galaxy has to accrete from outside
Before.
right? I don't know, but this would even energetically, I think, to put out such an amount of variance, because they should have been all in the disk originally, and then pushed out.
But there are winds. We know galaxies that.
I know, but we are talking about half of the. It's half of the variance. Now, I believe for the cold clouds could be these actually Fraternali. Filippo Fraternali is one of the authors. So it could be a galactic fountain. These clouds that then perhaps they refall or whatever.
Yeah.
But this extended medium, I don't know. I don't know if you can make it by just ejecting it from.
And has anybody calculated the limit of how much gas you can produce in this way? And how much gas you can retain in the cell in this way?
I think hydrodynamical simulation do, but they're all, they depends, there are billions of problems of convergence. They change, so depending on the resolution of the simulation, you can get one answer or another. And actually now what is trendy to think, what simulations will tell you, no, variance, because they put lots of feedback, of course. They put lots of feedback by hand. And so the variance should be all in the intergalactic medium, not even bound to the galaxy anymore.
Yeah.
So I don't know, but then, yeah, I don't know. If this is representative, it would seem like most of the variants are within 1 million radius. Not all.
So do you have any question from the Zoom?
They are all sleeping.
Okay.
No, we're still here.
Okay, so if we don't have any other question, let's thank Fabrizio again.
Thank you.
Fabrizio will be around for another 2 weeks, I guess.
A bit less, 10 days.
10 days. Okay.
Okay, thank you very much,
Okay, thank
Fabrizio,
you.
and
Thank
thank
you very
you, everyone for joining. So see you next week.
Thank you.